Hi, welcome back to Introduction to Computer Networks at NTU. I'm Polly, your instructor. Let's go over the assignments during this week. So we have PA7, as already reminded last Thursday, PA7 due. And we will have, hi Sylvain. And I see Emily tries to join the Google Meet session. No, guys, not yet. Okay, we are not yet starting the quiz 26. Okay, so we have a couple of videos to play before. Okay, we'll play the game. Okay, the quiz 26. All right, so back to the assignments. Hi. So PA7 will be due this Saturday, and there are 5 quizzes to submit this week. But no worries, all of them are straightforward. In fact, 3 of them are in a series. Okay, so I decided to expand one of the quizzes this week to 3 so that we can take one problem at a time to make it a little bit simpler to tackle. Okay, one smaller problem at a time. All right. Hi, Miguel. That's a very enthusiastic hi. Hi, I guess. All right. Or maybe that's a hi in the middle of it. You see that exam 2 is coming up in 2 weeks. Okay. And guys, exam 2 is going to be a little bit longer and a little bit more challenging. Okay. Guys, so next week, Polly is going to be on business travel. So there are no lectures, no live streams. But you do want to go over the live streams from last semester to cover the scope, okay? And so you might want to start studying, okay? So exam 2 is going to be a little bit longer and a little bit more challenging because exam 1 might be a little bit too simple. And I can see that there's a bunch of you that are in the 90s and 80s, and that's an indication that the problem sets are not exactly challenging enough. All right, okay. All right, so that's what's coming up next. I know you can't wait, so why don't we just go ahead and start with the lectures. Okay, so the first topic is congestion control. Okay, congestion control on the internet. Okay, so last week, a quick review. We finished talking about TCP's reliable data transfer mechanism. And we know that it's essentially go back in with a few improvements, isn't it? That's great. So that is one of the top problems in computer networks that we need to address. How do we do reliable data transfer? Congestion control is yet another top problems that we need to address on the internet. All right. And so in fact, the quiz that we ended up with last Thursday, right? You guys are asked to pretend to be an Uber driver. Well, you know, as I can tell from your answers, some of you are probably really Uber drivers. Yeah, good for you. So you guys are asked, you know, in case you drive into a highway that's highly congested, right? So you're part of the congestion. If you think about it, you being a driver taking your passengers to the airport is also a source of the congestion. And the other drivers who are about to take their passengers on the highway will be other sources of the congestion if they indeed join the traffic, right? So when you have a congestion, the way to mitigate it is first, like you guys did, right? Find out a way to notify, communicate with the other sources. Hey, guys, don't come. It's only gonna make the situation worse, isn't it? Yeah. So detect and send notification. Okay. Second is when these other sources receive these notifications, they can probably find ways to go around or wait a little bit, slow down, okay, before taking their passengers to the airport. So essentially, there are all these general approaches addressing congestion control will have very two important elements: detect and notify. Second, slow down or control somehow. Okay. Now, there are two flavors of congestion control we'll talk about. These are used for communication networks in general. The first one is called the end-to-end type of control, and this one is used by TCP. So let's check out how TCP, the principle of TCP doing congestion control. It's about 4 minutes, this first video.
With the scenarios elaborated, you see, particularly in scenario 3, the only solution or the only effective solution to a congestion is to what? Just slow down. And therefore, the two key design elements in a congestion control mechanisms are these. First, detecting when a congestion is occurring. Second, notifying the traffic sources that's causing the congestion to slow down. And there are two major approaches allowing us to achieve those. First is called the end-to-end based approach, the other, the network-assisted approach. Now, from the name of it, you probably guessed. Yeah, end-to-end meant the end systems are doing much of the work, detecting congestion, informing the traffic source to slow down. Network-assisted, on the other hand, is asking the routers to do all these work instead. Let's first focus on the end-to-end approach. So in this approach, the end systems will need to infer if there is a congestion occurring inside the network. If you recall back in TCP, okay, what we're doing is sending multiple packets in one flight to the receiver. Receiver sending ACK back. And all these packets and ACKs carry the sequence numbers. So receiver can actually detect a gap, okay, in the packets being received, and therefore sends duplicate ACKs instead of new ACKs. So receiving duplicate ACKs is a way of detecting if there's a loss, or the sender side can simply time out and then retransmit. That's also a signal of detecting there's potentially a congestion inside the network. So that is, observing from the loss occurring, inferring there's a congestion. One can also observe if there's delay changes. Okay, so for example, when we send packet out, let's track the sending time. Okay, let's track also the time when the ACK for that packet comes back. Calculate the difference, you get the round trip time. And if you observe for a long enough time, you might see, oh, the round trip time is increasing. When it goes beyond a certain threshold, then you could say that, also, network is running into a slight congestion there. Okay, so overall, general mechanisms, observe packet losses. If there is an increasing trend, observe the delay. If there is an increasing trend, then you're going into this hotter zone where congestion is likely occurring. Now, taking this approach, we do not get explicit feedback from the internet, from the routers inside the internet. And taking the end-to-end approach, we'll have to also guess or infer the right sending rate. Okay, so this is for the source to know exactly what is the right rate to send the data so that we do not overwhelm the network, in the meantime not being too conservative to slow sending the data out. Okay. And this is actually rather hard to do for the end systems. After all, they're actually at the very edge of the network. The congestion could be happening anywhere inside the network along the path. So what the end-to-end approach is doing is this, okay, guessing. By trying a certain rate and observe if there's a loss. Okay, if there's a growing delay. If not, then cool. This is actually within the available bandwidth. So maybe let's raise the rate a little bit and see, right, if there's a loss now, if the delay increases now. If not, then hey, we're still safe. Let's, increase it so that we're not too conservative, too slow sending the data out. Now, but if we exceed a certain point, and as a result, we begin to see loss, and we begin to see the delay increasing drastically. Yeah. That is actually not good. That indicates that we are probably exceeding the available bandwidth threshold, and therefore we are sending data too much, too fast into the network. So if we are failing, if we are detecting the signals of congestions, then that's slowed down. Okay, so end system here to infer, to find out what is the right sending rate is by trying. Okay, pushing. If we over push it, let's come down again and then try to push it again. Well, if not good enough, slow down again. So this is in fact the approach also taken by TCP. This is actually very natural because TCP being a transport layer protocol, it's actually implemented receiving side, sending side both at the end systems. Therefore, it implements an end-to-end based congestion control mechanism.
Yeah, so as you can see, this approach is almost like, your Uber driver friends, okay, waiting at the starting point and trying to observe, okay, how fast the other Uber drivers went to the airport and back, and how long it takes for the earlier drivers taking passengers to the airport and back takes. Yeah. So trying to detect or infer whether there's congestion inside the network, and try to take actions, okay, to avoid the congestion. Now the other one is exactly what you guys try to do, okay? You being in the middle of the traffic, in the middle of the network, seeing a congestion, okay, seeing the buffer is close to full, and trying to notify the ends to slow down, okay? Yeah, Justin, I saw your question. We'll come back to that after we play this video. So this is the other approach, the network-assisted approach. So we do things in the middle of the network, detecting and notifying, both in the network.
The network-assisted approach. Okay, so in this approach, routers will be doing the congestion detection. But how? Well, we also need to observe something, but this time we could actually observe something that's very directly related to congestion. This, the queue size. Okay, so this is the queue of these packets gathering at the entry point of the router. Okay, so congestion is this: sources of the traffic sending data too much, too fast into the network. Inside the network, we have these routers, right, handling packet forwarding. If the outgoing rate is slow and incoming rate is high, then these packets will need to what? Be buffered temporarily, okay, at the entry point of these routers. And therefore, they get a chance to wait for their turn to go out on the outgoing link. If the outgoing rate is slow, incoming rate is high, queue gets long, and free buffer space gets small. Right? So queue size or free buffer space, okay, changes of these, okay, are good indications of a congestion occurring. Now, routers, however, are the devices in the middle. Okay, how do the routers inform the sources so that the sources know that they need to serve them? Yeah, this is the way it's done. Okay, so there are these bits, special bits, okay, inside the packets. So when these packets travel through a router, and the router is so busy, queue size is so big, or free buffer space is so small, these bits get turned on. Okay? And when the packets arriving at the receiver, receivers can check these flags or check these bits and then inform the source of the data, the sources of the packets. Okay? Now, in internet, okay, the TCP/IP protocol suite. Okay, yeah, let me explain. Yeah, TCP is actually a transport layer service. Okay. But sometimes we also call the transport layer the TCP layer. IP is actually a network layer protocol, and therefore, sometimes we actually refer to the network layer as the IP layer. So TCP/IP here is actually referring to the internet protocol stack because the transport layer is running TCP. The network layer is running IP. So these two are the very typical classical protocols that are running, okay, supporting the operation of the internet. So in TCP/IP, or in internet, we have these special bits, and we call them the explicit congestion notification bits. So when the router inside the internet, the queue size gets large enough, or the free buffer space gets small enough, we set the ECN bits on. And therefore, the receiving end, the TCP receiver there, seeing the ECN bits on, can inform the source to send them. Now, that is how the routers in network-assisted approach detect congestion and notifying the source of the congestion. What's nice about this approach is this: the routers there observe exactly how much free space there is, okay, and dividing by the number of flows that's going through, number of connections that's going through. Hey, routers can also be more explicit, telling the receiver to inform the source. Now, set the sending rate to this size. Set your sending window size to a particular size, such that we will not be overwhelming, the router buffer space. Just like the flow control mechanism, right? Receiver there observing the receiving buffer, depending on how much is free, set the sending window size accordingly, and voila, problem solved. Receiving buffer will never be overwhelmed. Similarly, the router's receiving buffer here will never be overwhelmed.
Okay, so that is the network-assisted approach. To tell you the truth, there's actually an option in TCP called the ECN option. Okay, that is doing the congestion control in this network assisted approach. It's just that that option is very often disabled. Okay. So general approaches of doing congestion control on the internet. And now we move to the next topic, which is TCP's congestion control. TCP, we already heard, it's the end-to-end approach. All right. And before we talk about how TCP detect there's congestion and notify the source of TCP connection to slow down or speed up, okay, those are coming up. I'm gonna use this quiz 26, to try to get you guys into thinking, okay? And let me bring up quiz 26. Okay, so we had a similar problem here, trying to guess the prices of a merchandise. Okay, TCP does congestion control. You might see very close to how the stage 2 contestants figure out the true price of a merchandise. Right? So let me just say first, yeah, this quiz is nicknamed "The Price is Right." This is one of Polly's favorite game shows. Okay, it's a lot of fun. Okay, so what happens on this show is that there'll be contestants lined up like this. Okay, so there are 4 teams or 4 contestants lined up. Okay, and they will be competing, trying to estimate the price of a merchandise. Okay, and each contestant, or in this case, you guys, each team, okay, will guess. Okay, and the closest guess and not exceeding the actual price wins stage 1. The winner of stage 1 will be invited to stage 2. Okay, and when the contestant is in stage 2, it'll be 1-to-1. So this guy with the gray hair is the game show host, and this is the contestant. Okay, so within 30 seconds, the contestant will keep guessing the price of a substantial merchandise, fancier merchandise, okay, until it's exactly right. And the game show host, in today's case, Holly is going to be the game show host, and I will provide hints. So you will guess a price. When I see that the price is higher than the true price, I say too high. If it's lower than the true price, I say too low. And we'll go on and on and on and on until you get the prices right, or when the time is up. So we have only 30 seconds. All right, guys. Let's go to the Discord channel W10 quiz 26. Okay, and this is how quiz 26 is gonna run. Okay, we are currently at stage 1. Okay, so there's no need to join the Google Meet session now. Okay, the Google Meet session is for the winner of stage 1. Okay, all right, so back to stage 1. Polly will post a merchandise on the channel. Right there, right here on the channel, okay? And each team will be given 1 minute time to discuss, okay, what the guess will be, okay? And Polly will start the timer. Justin, well, let's see, binary guessing, okay, whether it will work, okay? So, hey, that's back to stage 1, okay? Each team is given 1 minute to guess the price. When the minute is up, you will hear an alarm start sounding. Then, guys, type up your team number followed by your guess. Okay. Shortly, okay, and no editing of the guess. Once you type it up, you cannot change. All right. Shortly, Polly will post the true price. When the true price is posted, then you cannot guess anymore. So you don't want to wait for too long after that 1 minute to type up your guess. Okay. Now, in case there are 2 or more teams that have the closest and below the actual price guess, we'll take the earlier guess as the winner. So in a way that the earlier guess might be favored, okay, and eventually win the stage 1. And something, precondition, all the prices are in NT dollars. Okay, so they might be taken from Amazon.com. They were originally in US dollars, but Polly has converted to NT dollars. But I also tuned the price up and down a little bit with some random margin. So you will need to know the price range and to be lucky to win stage 1. Okay, and we'll do the whole game show thing twice. Okay, so in case you didn't get it right, win stage 1 the first time, there's another chance. And the teams winning stage 1 in the game show, you will win the merchandise, but for this quiz, you'll win 5 extra participation points. Okay, all right. So stage 2. Okay, we'll talk about stage 2 when we have the first stage 1 winner. Okay. All right. Are you ready? So first thing Polly does is to post a merchandise. Okay, so now here's the merchandise. You need to guess the price, to estimate the price. Yeah, it's a pair of shampoo and conditioner. Okay, so one of the daily items. So this is from Pentium. And this is not a commercial. It's just that Polly picked something random from Amazon. And hey, it's highly rated, 4.7 from 3,300 customers, satisfying customers, obviously. Okay, so guys, are you ready? You have 1 minute. Okay, let's start counting the time. Okay, that's 30 seconds already. There, 1 minute. Okay, guys, type up your answers. Okay. Guys. Okay, Polly is about to show the true price. Okay. Okay, time up. Polly is gonna show the true price. And ta-da! 581 NT dollars. Let's see. Okay, team 5, a contentant, 400, 250 below. Unfortunately, Justin, 750 is a little bit too high. Team 9, 740 is also a little bit too high. Hey, wait, team 1, 549. Wow, pretty close. Okay, I think. Wait. Team 2, oh my goodness, 580. Okay, team 2 is now the closest. Team 6, 600 is a little bit too high. Team A, 3. Yeah, I think. Hey, guys, team 2 is the winner. Okay, just off by $1 and nicely below the actual price. Okay, so team 2, you are the winner of stage 1. So both members in team 2 will receive 5 extra points for participation already, and you are invited to enter stage 2. Okay. Sylvain and Jeremy, I don't know which one of you would join the Google Meet session, but hey, you guys need to, pick one. I see Jeremy is here. But Jeremy, you want to mute your YouTube live session. Okay, just turn the volume of the YouTube session off. Yeah, because otherwise you might experience echoes. Hi, Jeremy.
Hi.
Hi. Hi, great. I can hear you. Can you speak?
I can hear you too.
Okay,
Yeah.
we can hear you fine as well. Okay, perfect. All right, so what I'm gonna do next is to post another merchandise, which is fancier, much higher price, and you'll be given a few seconds to breathe and to count down before starting. Okay, now whether you want to implement the binary search as Justin suggested, you have to decide now. Okay. When
That's fine.
when the time is very limited, it's probably hard to implement the binary search. Okay, all right. When Polly says "Let's begin," a timer of 30 seconds is set. Okay, and so when that 30-second is up, you will hear a long alarm sound that's really loud. Okay, and we'll stop. All right. So, do you get the point? Now let me.
All right.
Okay, that's let me.
Okay.
Great. Now let's post the second item, the fancy, super fancy item. Using the idea of binary search should still be the most efficient? Yeah, I agree. Hey, this is the item.
Can I start right now?
Not yet. I have to
Okay.
introduce the item, sorry, as a game show host. Okay, so this is, guys, the brand new PlayStation console, nicknamed the PlayStation 5 Slim. It is very hard to come by, but it would appear in the game show today. Okay, so it's supposedly lighter, slimmer, prettier. Okay, so Jeremy, that is the item that you need to guess the price for.
Okay.
Are you ready?
Yeah, sure.
All right, that's start, and I'm starting the timer. Okay.
Okay, 15,000.
Too low.
20,000.
Too high.
70,500.
Too high.
16,000.
Too low.
17,000.
Too low.
70,250.
Too low.
70,300.
Too low.
70,400.
Too high.
70,350.
Too low.
17,317. 75.
75? Okay, I think that's a very good guess because that's exactly the binary search. Middle of 17,350 to 400, right? So you know clearly it's between 350 and 400. And you guessed 375. Very, very logical guess. Okay. But it's just a little bit off. Okay. I mean, post the true price. $352.
Oh, terrible.
Yeah. So I guess you see also that as human beings, to try to do the binary search is a little bit hard to be fast. Plus, it takes also time to pronounce the price, right? Very nice try. Exactly. You are very close. Okay. And I think by being like $2 off, okay, I'm gonna award you and Sylvain. I think both of you are in team 2. Half, okay, of the supposed prize. So suppose if you win 20 points, you guys earn 10 points. Okay?
Thank you.
Congrats! Yeah. All right. Thank you. Okay.
Bye.
Bye. And so, how about we play the game again? That's a ripoff. You know what? It's not officially on sale yet. Yeah, Zhenyu. It's not officially on sale yet, but there are a few items, okay, people that are, putting up. And I think the actual price, and I got this from the Japanese website, JapaneseAmazon.com. Yeah. So they are selling these in 78,000 Japanese yen. So if you are interested in getting one, go to the Japanese Amazon. All right, so hey, how about we play the game again? I think you guys are getting a hang of this. All right, so guys, let's go back to stage 1 again. Let's do this again, okay? So let me post a everyday item once again. Okay, and this one is probably not that everyday. Yeah, this is the Pokemon Encyclopedia, the latest version, updated 2022. Yeah, it's also highly rated 4.8 by 515 satisfying customers. All right, so teams, you guys have 1 minute, okay, and discuss, okay, for the prize. And that's start counting time. Hey guys, this is in NT dollars, okay? All right, guys, time's up. Yeah, all of you type up your guess. 3, 6, 14, 5. Okay, guys, I'm gonna post the price now. All of you. I think there's one team. Yeah. Okay. Good. So all of you posted, and guys, all of you are too high. Okay, all of you guessed too high. It's not that expensive. Okay, I got this from the Japanese Amazon as well. Okay, so lower your price, lower your price. Okay, let's try this again. Another 1 minute. Lower the price. Okay, one more time. 1 minute. Okay, guys, time's up. Okay, put your guess there. All right. Okay, good. So let me post the solution or the actual price. Yeah, it's 7:48. Let me see. Ah, okay, Justin, you're close. Oh, Zhexuan is even closer. 7:40. You know what? Yeah, Zhexuan. And I think Zhexuan is Team 9. You guys won stage 1. Okay. Zhexuan or one of you guys in Team 9, please join us in the Google Meet session. Okay, please call in. I hope you're prepared to join. Okay, Team 9, you won. There you are. Zhexuan, mute your YouTube session first, okay? All right, Zhexuan, could you talk? Uh-oh, we are not hearing you.
Yes. Very good.
Oh, okay, I hear multiple voices. Okay, great. I guess the team is there to support you. Very good, very good. Now, let's upload this item. Okay, that's very fancy. Yeah. All right, so this is a sound bar. Okay, it's an item that one must have for a sizable living room. Okay, where you have a sizable TV. All right, and it's top of the line from a company called Sonos, who has mastered stereo systems. Okay, such as a sound bar. All right, so this is the item. Okay, and let me prepare the timer for 30 seconds. All right. Are you calm now?
Yes.
Okay, good. So let me start counting time and begin guessing, Zhexuan.
2,000,
2,000 too low,
10,000,
too low,
15,000,
too low,
20,000,
too low,
30,000,
too high,
25,000,
too low,
27,000,
too low,
28,000,
too high.
27,500.
Okay, that's a good guess, right? Again, you know it's in between 27, 200 to 300. Therefore, you guess. Sorry, you know it's between 27,000 to 28,000. Therefore, you guess 27,500. Yeah, so very close. But again, missed just by a little. Okay, let me post the true price. Yeah, this is the true price. Okay. Yeah, similar to the last group. Yeah, we are getting really close. Yeah. Okay. So again, just like team 2, you guys will receive 10 points, extra points. So winning stage 1 is 5 points already. Winning the second, being close in the second stage, you also get 10 extra points. Okay, congrats. Yeah, I see. Yeah, bouquets. Thank you, Zhexuan. All right.
Thank you.
Great. So I guess you guys get a hang, right? Guessing what is the right price. In case you can get a signal suggesting your guess is too high, too low, you can try to adjust, right? The other way. You know what? That is exactly what TCP's congestion control mechanism is trying to do. And that mechanism is called AIMD. Okay? When it's too low, it adds the sending rate incrementally. When it's too high, when the sending rate is too high, it will decrease the sending rate multiplicatively. Okay? Elu will come back to your comment maybe. Okay. Yeah. Okay, Elu will come back to the comment after we play this video. So this is how TCP adapt to congestion signals. Okay, TCP infer from the source.
And we'll take a look at an example of an end-to-end based approach, TCP's congestion control mechanism. And TCP does it this way. The sender will increase the sending rate gradually if there are no packet losses detected. But as soon as there's a packet loss, we drop the sending rate drastically. So point number one here, packet loss is used as an indication of network congestion in TCP. Point number two, TCP is actually implementing a trying failing process to discover what is the proper sending rate. Now, by sending rate here, I'm adjusting. In TCP, it's implemented this way by changing the sending window size. You see that the sending window size is a limiting number of bytes we can send out within one round trip time. Therefore, increasing the sending window size is increasing the sending rate. All right, the exact process of doing the trying and failing is called the additive increase multiplicative decrease, or AIMD to be short. So AI describes the increasing process of the sending rate. So this is done by setting the window size and such that it increase one packet per round trip time. And the decreasing part is this cutting the window size to half of it, okay, after detecting a packet loss. So you see the increasing part is slow and linear. The decreasing part is drastic, multiplicative. So additive increase, multiplicative decrease. Okay. Linear increase, multiplicative decrease. So if I show the sending window here over time, we'll see when there are no losses, the window size is going to grow linearly. As soon as we hit the loss, we drop the window size drastically to half of it. So additive increase, multiplicative decrease. So each of these AIMD episodes looks like a sawtooth. And that is why people often say TCP's window size change over time shows a sawtooth behavior. One thing I want to add is this. We say we increase the window size by one packet per round trip time, but TCP sequence size is counting data by bytes. Window size is therefore also counting the maximum amount of data we could send out by bytes. So what do we mean by increasing the window size by one packet? That doesn't make sense. How do we implement that? Yeah, so the fact in the implementation, what's being done is to increase the window size by one maximum segment size. Okay, so MSS here, if it's configured to be 1460 bytes, then the window size is incremented by 1460 if there's no loss detected within a round. And this is actually related to the second point I want to stress. Yeah, you see here, the full name of the sending window is no longer WND. Right? It's actually called the congestion window size, CWND. Because the sending window size is dynamic in TCP, and it's actually controlled by the congestion control mechanism. That's why the window is now referred to as the congestion window. And this is TCP's process of trying to probe and discover the available bandwidth. Now let's bring up the diagram we used to explain TCP. Now it's counting bytes. Now each of these is what? A byte. If we'll be generating a new packet, then we'll be using the byte stream number here as the sequence number of the new packet. Right? So what you're seeing here is I'm updating the diagram such that this term here is no longer WND, the sending window size. We are now calling it the congestion window size, okay, because this here, okay, CWND is dynamic. It can be large or small. It's no longer a fixed size. And how large it is depends on how the network is smooth. How small it is depends on how bad the network is congested. And the quantity CWND here limits the number of bytes there can be between the last byte sent to the last byte act. Last byte act. So green here are counting the bytes that have been sent and have been act. So the last byte act is the last screen. Yellow here are the packets sent or the bytes sent but not yet act. So last byte sent is here, the last yellow. Okay. So last yellow, okay, subtracting the number of the last screen. That means the number of yellows. Okay, so CWND here limits the number of yellow bytes there can be at best. Last, so we say TCP's congestion control is done by controlling the sending rate or changing the sending rate to discover what is the right one. Okay. We already mentioned earlier that is actually implemented by changing the window size, changing the congestion window size, because the sending rate is essentially the congestion window size divided by RTT, because within a round trip time we can only send these many bytes.
All right, so you can see from this video what is the indication of the transmission rate or congestion window size currently too small. I'm sending data and I'm receiving the X okay, smooth. Okay. Observing no loss, that's an indication of saying that the current sending rate or current congestion window size is too low. So increase the congestion window size. Okay. When the TCP source detects a packet loss, for example, by having a timeout or having a duplicate ACK, then decrease the congestion window size, which means the sending rate. Okay. Now, guys, you guys knew that to guess the price of merchandises, it's better to do binary search. Is TCP doing a binary search here? TCP is very conservative, isn't it? Can you guess why? Right? It's adding increment linearly, dropping multiplicatively, okay, between 0 and the current window. Not the lowest window TCP knows previously. Okay, why? All right, so I'll let you guys ponder, and let me try to address Jeremy's question here. Okay, I mean, is there always congestion on the internet, or is it sometimes how to send at full rate without generating congestion, like in the middle of the? I see. Anthony, you're correct. Anthony, you are correct. Very good. Jeremy, yes. When the destination you're sending traffic to, okay, between you and the destination, there's just not much background traffic. Chances high that you will increase the congestion window size until the maximum, okay, the default maximum defined in a TCP connection. Yeah, that can be very high. Okay, but that default maximum could differ from operating system to operating system. And some people might compile a customized version of TCP to make the max window size even higher. And that I have seen people doing to exchange data between data center to data center. And all the middle networks, they are sure that there's enough bandwidth in order to do high volume TCP connection. Yeah. So Jeremy, yes, it's possible. Anthony, yes. If you have taken courses about control or control system, you knew that, hey, one TCP connection is not the only traffic existing on along the path of that TCP connection. There could be multiple TCP connections, meaning there are background traffics. So the available bandwidth can change from time to time. So even though you are increasing slowly, there could be another connection, such as Jeremy wants to send, okay, that arrives suddenly, okay, And so it's not exactly good to change the sending rate all that drastically, especially the increasing part. It's very easy to induce congestion if we increase aggressively. Decreasing being aggressive, that's okay. Right? So once everyone is friendly to each other, then we would try to slowly seek for the optimum rate. Okay, increasing the sending rate gradually together. Okay, that is why TCP does it in AIMD. Okay, great questions, Jeremy and Anthony, or actually great comments from Anthony. And you know what? That's all the time we have. The next topic is called TCP slow start. I'm afraid that we'll talk about that tomorrow. So AIMD is the control TCP does in the steady state. Okay, when the TCP connection just starts up, it always starts from a window size that's 1 MSS, which is very small. Okay, so this slow start is the mechanism to increase from 1 MSS to like the steady state, okay, projected transmission rate. Okay, so that process is called slow start. And tomorrow you'll hear that it's actually not slow, it's very aggressive, more aggressive. The way it increases the window size, the congestion window size, is more aggressive than AIMD, what TCP does in the steady state. Okay, so very counterintuitive name, slow start. It's in fact fast start. So we'll talk about that, and I will see you tomorrow morning. Okay, thank you guys for participating in the game. Okay, I had a lot of fun. I always wanted to be a game show host when I was growing up. It's so interesting. All right, it's a lot of joys watching you guys, winning something. Okay, so I will see you tomorrow. Okay, bye. Yeah. Yeah, and you guys get the point. Yeah, guessing a price, guessing the sending rate, how that can be done.